Alrighty, CNT120, we are looking at Chapter 6 on wireless networking. Here are the couple objectives we have for this. We want to talk a little bit about the characteristics of wireless transmission, standards, how to plan out, set up, secure, and even troubleshoot a Wi-Fi network. And some of these last ones down here will be ones we're going to be doing in our lab this week, whether you're on campus or online. Alrighty, first thing we want to look at is characteristics of wireless transmission. So what we need to remember was with wireless transmission, our signals are getting transmitted through the air via radio frequency waves. Any wired network is going to be using copper cable with electrical, voltage pulses, if you will, or fiber optic cable using pulses of light. But with our wireless networks, we're using radio frequency waves going through the air. Now, from there and above, if you will, wired and wireless networks are similar. Anything layer 3 and above is all going to be similar, using IP, TCP, and UDP protocols, and those sorts of things moving up. It's just a layer 1 and 2 that is different from wired to wireless. The nature of the atmosphere that we're transmitting our signal through is different. That's going to affect what happens with our wireless signal. And most of us kind of know that already from we'll have a good connection one place, we move to a room, connection gets lousy, or move to another room, it gets lousy. We kind of know that. The atmosphere affects our wireless signal, unlike wired transmissions. As long as I'm plugged into the network, I have a good connection, if you will. They mentioned at this point Internet of Things. They did it real briefly, but I just wanted to remind us with Internet of Things, we have all kinds of things that we connect to our network now. You go back 10, 15 years, you would have maybe a laptop, maybe a game console connected to your wireless network, but there was not much else. Today we have our laptops and tablets and game consoles and cell phones and plenty of other devices in our house. Could be thermostats, other smart devices, whether it be, light bulb controllers or switch controllers or those sort of things. Plenty of things that are connected to our network now, and a lot of those fall into the Internet of Things. These kind of devices that are connecting to our network. And a lot of these are using wireless. Some of these are using Bluetooth for local connection, but a lot of these are actually using a wireless connection. Things like your Ring doorbells and cameras and smart speakers and those kind of things, and smart thermostats are usually using your wireless network. Now, when we deal with wireless networks, we have to remember it's part of the wireless spectrum, which is a larger thing. The wireless spectrum is the continual electronic waves used for data voice communications, range from frequencies lowest to highest, from 9 kilohertz up to 300 gigahertz. And our the wireless networking, if you will, is just a slice or a piece of the overall wireless spectrum. And because it is kind of a finite resource, there is only so many frequencies. In the United States, the FCC oversees who's using what frequency where for what purpose. You don't want to have two radio stations in the same town broadcasting the same frequency. You don't want to have two different devices in your house broadcasting on the identical frequency and conflicting with each other. So all this has to be kind of doled out and planned. So in the United States, the FCC oversees that. Anything that's crossing borders, country borders, if you will, is usually being overseen by ITU, International Telecommunications Union, which interestingly enough is a subgroup of the United Nations, the UN, because we do need to coordinate between different countries. Here's just a picture I've held on to for a number of years about our electromagnetic spectrum, giving you an idea that it ranges anywhere from our radio waves up to infrared, up to X-ray, gamma rays, etc. That's the whole electromagnetic spectrum. Well, the area that we're concerned with is kind of in this area right here, just this little slice of our electromagnetic spectrum, the wireless piece, if you will, just this part down here. That's where our communications for our devices, our wireless networks, that sort of thing will be occurring or do occur. The book breaks it down even further and just looks at that wireless spectrum just in that piece, just kind of this piece here, and breaking it out further and showing you things like RFID, things like our Wi-Fi, Bluetooth, other RFID bands, and other Wi-Fi bands as well. These are the areas that we typically are using, or the frequencies we're typically using. The book mentions some of these, so I put them all in a chart for us here for quick reference or easy reference. It almost took this chart here and broke it out for you and kind of spelled them out a little bit further, showing you where RFID, cellular, a second RFID band, other cellular band. Most of our Wi-Fi is in the, I should say, one of the first bands of Wi-Fi is in the 2.4 gigahertz range. Our other one is in the 5 gigahertz range, and then we're having a 6 to 7 gigahertz range as well for additional Wi-Fi. So just kind of giving you a breakout of where these frequency ranges are. I'm reminding you super quickly about Bluetooth. We all use a lot of Bluetooth things, and it is part of our bigger spectrum, if you will. Bluetooth for a lot of us is kind of that wire replacement, connecting a smart device to a phone, whether it be a watch or other sensor, another meter or whatever that I'm using to my phone to my laptop, phone to my car, that sort of thing. A lot of us use Bluetooth. It's defined by IEEE 802.15.1 specification, and it's actually named after medieval king of Denmark, Harald Bluetooth, who fought to merge several Danish tribes together. And actually, if you look at the Harald Bluetooth, the Norse lettering for Scandinavian lettering for, when you combine those two, that's how you get the Bluetooth symbol. This would be a little interesting, informative speech for a class, or even an informative paper that you have to write. A lot of people use it, don't know where it came from. And there's even a legend that he ate a lot of blueberries, so hence he had blue teeth kind of thing. That's one of the legends about it. This, like we said before, is for a lot of us, kind of like the cable replacement, if you will. Close proximity for things like smartwatches, headphones, car, a lot of devices in our house, etc. Most of our devices, laptops, etc. have it built in. All we need to do is enable it and pair up our devices. So it is part of our wireless spectrum. We should at least remember it's there as part of our bigger spectrum. One of the other things we should remember that is there is our RFID. There's some things we use in RFID that we may not think about, but we do use, and they are part of our wireless spectrum as well. Radio frequency identification. This has been used a lot of different ways. Again, it's in the frequency bands here. Okay, and it can actually hold a little bit of data and can be referenced if needed to either get information off of or verify the identity of something. Things will hold like serial numbers, credit card information, even medical data. A lot of times used for inventory management, can be used for other things as well. A lot of us are familiar with, driving toll roads and using something like an Easy Pass, where it's actually just charging our account for you instead of stopping and handing money to a toll booth worker. That is RFID. Some warehousing facilities use RFID for product location. Where is it? I know in hospitals they use RFID chips and inventory controlled devices on things like IV poles and so forth. Where is this specific piece of equipment? And here's warehousing as well. There's been a number of interesting applications over the years. Some were useful, some were cost prohibitive, but identifying identifying tires for a race car on a certain race to making sure they're not, slipping in another secret tire kind of thing. I know some casinos were using RFID tags inside their casino chips to help with people counterfeiting the casino chips. And some of us even know we use RFID chips in things like our pet tags, where they put them, kind of up above the shoulder blades as a little chip to identify in case they're lost. All those are applications for RFID, and there's plenty more. I know at one point Walmart was looking at, and other large big box stores were looking at putting RFID tags on all their products, and the idea being you put the couple things you need in a bag, and you literally walk out the door. The scanner would pick up those tags and then actually pick up, like in your pocket on your key ring, a little tag, and it would say, okay, this guy Doug Brown, there's his key ring tag, bought these 3 things and just charge it to my account for me. Neat, technologically really cool, really neat. Unfortunately, the cost of a lot of the RFID tags were more than the actual product itself. You think about buying a pack of gum for $1 or $2. Well, sometimes the tags were more than the cost of that product. So in many cases, it was cost prohibitive. So they've used them in certain applications for maybe high dollar items or high theft items to try to prevent that sort of thing. When we deal with wireless, we have some channel management we need to deal with. So we have that frequency band, we might have different channels to communicate on. There's been different ways to do this over the years, and at different times, different wireless technologies have used one or the other. This is where they mention the frequency hopping spread spectrum and the direct sequence spread spectrum. Frequency hopping spread spectrum is you have a, let's just say 10 channels, 10 frequencies that you're going to use, and it will broadcast on one frequency channel, we'll just call it channel 1 for a little blurb of time, then jump to another channel, channel 10, send a little blurb, then jump to 5, send a little blurb, then to 2, send a little blurb, then to 9, send a little blurb. And the idea was, if there's any interference, this is hopefully hopping around this. That was the idea behind this. This was actually developed from something else. I'll give you a little tidbit here in a second. This was developed from something else that was on that line. So here's your frequency hopping spread spectrum. Over time, you're jumping between different frequencies as you go and sending a little bit, then sending a little bit, then jumping, sending a little bit, and jumping. And the sender and receiver know the frequency that they're jumping between, if you will. And again, here shows the same idea. Over time, a little bit in this channel, then this one, then this one, then this one, then this one, this, and so forth, and just hopping as you go. And I think this is a picture they use in the book here for you as well. Jumping between these frequencies, bouncing back and forth. And the idea is you're trying to avoid any sort of conflict or noise that might be in your in the area that you're transmitting in. Now, the interesting tidbit here is this was developed, adapted from something that was developed back in World War II. There was an actress by the name of Hedy Lamarr, very famous actress, but also a really, really brilliant engineer. She and another person, she was on the creative, and sadly, she had the idea, but they had to have a man actually apply for the patent, otherwise they wouldn't have taken her seriously, which is really sad. But she patented the frequency hopping spread spectrum idea, and it was designed for torpedoes. The idea was they were hopping around, send a guidance for the torpedo on one frequency, jump over to another frequency for a little bit, then jump over to another one. And the idea was it was making it harder for the enemy to jam or either detect or jam that signal and block that torpedo from hitting its target. So this is a way for the enemy to make it much harder for the enemy to even detect what you're sending, let alone if they find your frequency, it's only for a brief amount of time, and not be able to jam or take control of your torpedo. And that technology is what evolved into what got used for these wireless transmissions. Fun tidbit. That would be another interesting informative speech or informative essay that you might need to write for a class. The other technology is direct sequence spread spectrum, where you're basically broadcasting over the whole frequency band, over all the frequencies at the same time. The process dividing and coding the data, called chipping, spreading that out over the whole frequency band as it sends. It uses the available info more efficiently, and tends to have a little bit higher throughput than your frequency hopping spread spectrum, because we're spreading it out over the whole frequency band and sending, kind of consuming the whole bandwidth. And here it shows you the whole. I'm using just that frequency, but I'm sending everything on that frequency band. So as we look at different wireless technologies over the years, some have used frequency hopping spread spectrum, some have used direct sequence spread spectrum to manage these channels and how we're sending our data from A to B, if you will. Another technology that has been adapted or evolved with our wireless transmission is channel bonding, where you used to have sending in one frequency channel. In some cases, they'll take these two channels and bond them together so you have a larger, almost like a larger lane of a highway to send more data through. So channel bonding has been used to increase the bandwidth of the signal that you're sending across the wireless link. All right, when we come back in the next podcast, we'll pick up and start talking about antennas.